Hi, welcome to lecture 2. Today we're going to talk about diagonalization, similar matrices, and then we're going to do a quick logic primer. Okay, let's just recall the last thing from last lecture, which is we call a square matrix diagonalizable if you can find an invertible matrix U and a diagonal matrix capital lambda such that A is equal to U lambda U inverse. And we said that you could find the columns of U were the eigenvectors of A, and the diagonal entries in lambda were the eigenvalues of A in the same order. Right, and basically you can do this as long as you can find n linearly independent eigenvectors to make the columns of U, which happens if and only if for every eigenvalue you have enough eigenvectors. In other words, the number of eigenvectors you have, the geometric multiplicity, is equal to the algebraic multiplicity. Okay, so let me just give you one example that's written in the notes. And it's the example that we did last time, which was reflection across the line y equals x. Right, so there the matrix was 0, 1, 1, 0. We computed that. And the eigenvalues we computed were plus and minus 1. And we even found bases for the eigenspaces. Right, so the eigenspaces E1 was the span of 1, 1. That was like the mirror. And E negative 1 was the span of negative 1, 1. Okay, so we did all these computations last time. And from this, we can conclude that the matrix is diagonalizable because it's a 2 by 2 matrix and we found 2 eigenvectors. That's because we had 2 distinct eigenvalues. Each eigenvalue gave us at least one eigenvector. And that gave us 2, right? So here, you can form the matrix U, 1, 1, negative 1, 1. And the diagonal matrix lambda should be you take the eigenvalues in the same order as you took the eigenvectors. And then since this is a 2 by 2 matrix, it's reasonable enough to write down its inverse. So what you do is you take 1 over the determinant of the matrix, right? So the determinant of this matrix is 1 minus negative 1, so it's 1/2. And then you flip the diagonal entries and you negate the off diagonal entries. So you can check, maybe I'll just do this computation here, that if you multiply these two matrices, you get 1/2 times 1 plus 1 is 2, 0, 0, 2. So you do in fact get the identity matrix, right? So that's the left inverse. And then you can check that you can write A as U lambda U inverse. Okay. Now, there are many applications of diagonalization, and the first one is one that you probably, actually, you talked about both of these things in Math 308, but we're going to try to understand them a bit better. The first application of diagonalization is taking powers of matrices. Okay, and the point is that if you can write A as a diagonal matrix, if you can diagonalize A by writing it as U times the diagonal matrix times U inverse, then if you want to compute some high power of A, then what you need to do is you need to multiply this matrix by itself k times. Right, you do this a total of k times. But U and U inverse, if you multiply these together, you just get the identity matrix. So everywhere on the inside, the U inverses and the U yield identity matrices. So what you get at the end is U times lambda to the k times U inverse. Okay, but the nice thing about a diagonal matrix is that it's very easy to take a power of a diagonal matrix, right? If lambda is equal to the diagonal matrix with all lambdas, lambda 1, lambda 2, lambda n along the diagonal, then the kth power is just the diagonal matrix that has the kth power along each of the entries. Right? You'll recall that taking a power of a matrix is a hard thing to do in general. If you have just a general matrix, you have to multiply it together k times, and that's not a very fun process. But if it's a diagonal matrix, then the formula is very easy. Right? And then you know what U is, you know what U inverse is, you know what lambda is, so it's very easy to compute a high power. Right? So if you take this matrix A and you want to compute it to a high power, pick any power you want. Let's take 2021. Well, since earlier we wrote A as U lambda U inverse, this is U lambda to the 2021 U inverse by the above computation. What was U? It was 1, 1, negative 1, 1. I just forgot, even though I just looked at it, right? Where the negative 1 was. And then it was 1 and negative 1. So 1 to the 2021 and negative 1 to the 2021 times U inverse. To be honest, in a second you'll see why it actually doesn't matter. And the point is that 1 to the 2021 is just 1, and negative 1 to the 2021 is just negative 1. So this is, in the end, just U 1, negative 1, U inverse. But this matrix here is just the same thing as lambda. So you just get A back again. When you raise A to the 2021st power, you just get A. Right? In fact, that's true for any odd number. For any even number, though, you'll get the identity matrix. This is what's happening. Okay, so this is genuinely useful. If you want to take a high power matrix, you don't want to multiply the matrix out. If you can find a diagonalization, then it's much easier to compute U inverse, take a high power of the diagonal part, and then you can compute the high power of the matrix. Okay, now this is like very, very useful thing to be able to take a high power of a matrix, but it's not really what diagonalization is. So that's next what I want to talk about is what is diagonalization actually? Okay. And the first thing that I want to observe is that a diagonal matrix has a very easy to understand action on vectors. So if lambda is a diagonal matrix, it has a very nice action on vectors. Right? If I want to multiply this matrix by this vector, what does it do? It just sends x1, x2 down to xn up to the vector lambda 1, x1, lambda 2, x2, down to lambda n, xn. What the diagonal matrix does is it just multiplies in each diagonal entry into the components of your vector. So a diagonal matrix is a very nice action. And the real meaning of diagonalization is that a diagonalizable matrix, sorry, something was rattling, behaves just like a diagonal matrix, as long as you're willing to change basis. Okay, so change of basis I find is one of the things that's hardest for students to understand in Math 308. It is actually covered in Math 308, but let me just remind you the following. So if a point in Rn has coordinates given by x with respect to the standard basis, which is the basis that we're all used to, let me give some notation. The standard basis will always be denoted E1 up through En. Then its coordinates with respect to the basis let's call it script U, vectors U1 up through Un of Rn, is given by y equals U inverse x, where U is the vector, is the matrix whose columns are given by these basis vectors U. This thing is called a change of basis matrix. Okay, what do I mean by that? What I mean by that is we are all used to working with the standard basis, right? So if I take the point, let's say 3, 5, we all understand that point. Maybe I shouldn't have picked such big numbers. To a mathematician, 5 is a big number. We all understand that I'm talking about this point 3, 5. Now, why do we understand that this is the point 3, 5? Because this point is 3 times 1, 0 plus 5 times 0, 1. Or in other words, 3 times e1 plus 5 times e2. So whenever I give you a vector normally, I'm talking about a vector with respect to the standard basis of Rn. But the standard basis is not any better than any other basis. So if I take a different basis, let's now take the basis from the other day and the first example of this class, where the basis vectors are given by 1, 1 and negative 1, 1. The point is that every vector in the plane can be written uniquely as a linear combination of 1, 1 and negative 1, 1. So this point that we usually call 3, 5, if we all lived in a world where the red basis vectors were our basis, we wouldn't call it 3, 5. We would call it its coordinates with respect to this basis. What this theorem thing, definition theorem, it's a definition slash theorem, tells us is how to find the coordinates with respect to some other basis. Right? So what you do is you take U is the matrix whose columns are your basis. U inverse we computed earlier, it was 1/2 times this matrix. And what this theorem says is that if I multiply this matrix by my vector x, I will get the coordinates with respect to the basis U. So let's do that. Right? So what is U inverse times 3, 5 here? It's 1/2 times 1, 1, negative 1, 1 times 3, 5. So I see that you get 1/2 times 8, comma 2. In other words, it's 4, 1. And maybe this picture isn't that great, but if you go 4 times in this direction, I've gone a little bit too far, and then 1 time in this direction, you do in fact get 3, 5. Right? In other words, this vector could also be written as 3 times u1, sorry, not 3, what am I saying? 4 times u1 plus 1 times u2. If we all lived in a world where this basis u was the basis, then we wouldn't call this point 3, 5, we would call this point 4, 1 with respect to the basis u. Okay, so if you want to go back to, if I now have a point with respect to the basis u, and I want to understand what is that with respect to the standard basis, instead of multiplying by u inverse, you would multiply by u, right? Because if y equals u inverse x, then of course this is this, since u is invertible, is the same thing as saying that x is equal to uy. Okay, so there's a u appearing in a diagonalization, there's a u inverse appearing in a diagonalization. A diagonalization is really about change of basis, right? So if A is diagonalizable via A equals u lambda u inverse, then when you multiply by A, it's the same thing as multiplying by u lambda u inverse, right? So if x is any vector in Rn, then A times x is u lambda u inverse x. Well, what is u inverse x? U inverse x is like writing x with respect to the basis, the eigenbasis. This is like y equals u inverse x. This is writing x. This is the point x with respect to the basis u. Then what does lambda do to that? Lambda just acts like a diagonal matrix because the basis consists of eigenvectors, right? Of course, lambda times u1 is just, okay, what I should say is lambda times 1, 0, 0, 0 is just lambda 1, 0, 0, 0. In the basis, I mean, here it's like I'm imagining that this is in the basis B, right? Because it's you took u inverse x. So if you took the first standard basis vector, if you took the first basis vector of u, if you took u1 and you applied u inverse u1, you would get exactly 1, 0, 0, 0. Because the vector u1, if we were all living in the world where u was the basis, we would call it 1, 0, 0, 0, 0. Then when you multiply by lambda, it just scales it. But of course it just scales it because u1 was an eigenvector of a. A just scales it. Right? So this is like what you're doing to the vector u inverse of x is you're doing like a diagonal thing to it. You're just scaling each component. So let me maybe do this in red. This thing is like lambda applied to u inverse x. But we don't live in a world where the basis is u. We live in a world where we have the standard basis. In other words, when you write a vector x, when you write a times x, you really mean a times x with respect to the standard basis. And so this last u now converts you back to the standard basis. So green converts back to standard basis. So the point is that A acts like a diagonal matrix on a very special basis, right? A times ui is equal to lambda I times ui. So if you let u1 be a basis vector, then u1 is just the vector 1, 0, 0, 0, 0, 0, 0. And what A does to it is it just scales it by lambda, 1. Okay, so another way that it's written in your notes is if you want to understand ax with respect to the basis u, right? So another perspective, trying to give you more than one way to think about this. Let's live in a world that's always uses the basis u. Then if I, who live in the world with the standard basis, give you a vector x, you would understand it as u inverse x. And if you want to know what A does to this vector, you would want to know u inverse of ax, right? U inverse of ax, right? So I give you the vector x and the vector ax. I say, here's the vector that I started with. Here's what A does to it. Here's ax. You live in a world where the basis is u. So to you, these vectors are u inverse x and u inverse ax, right? But of course, u inverse ax is just u inverse times u inverse x, right? Because, what am I saying? This is just u inverse times A is just u lambda u inverse. That's all A is, right? All I've done is I've just replaced this A with this. And that's the same thing as lambda u inverse x. But again, the vector that we would consider with respect to the basis u is actually u inverse x. That's y. This is just lambda y. In other words, if we lived in a world where the basis was just u, then what the transformation A would do is it would always just send y to a diagonal matrix times y. So A acts just like a diagonal matrix, just in a different world where the basis consists of the eigenvectors of A. This is really what diagonalization is. Diagonalization is saying that A acts like a diagonal matrix with respect to a different basis. Okay, in fact, this notion is more widespread than just diagonalizability. This brings us to our next topic of similar matrices. Okay, and this is the first actually new thing in the course. Okay, so here's the definition. Two matrices, A and C, are called similar and we denote this with a tilde, A is similar to C, if there exists an invertible matrix B such that A is equal to B, C, B inverse. Okay. Now, new definition. We need to have some examples. We need to think about what it means. Right? So here, I'm saying that A and C are similar if you can find an invertible matrix such that A is equal to B, C, B inverse. This should remind you of diagonalization in some way, right? So the first example is if A is diagonalizable, then you can write A as U lambda U inverse, where U is invertible and lambda is diagonal, which means that A is similar to lambda. So the definition of diagonalizability is just the same thing as saying a matrix is diagonalizable if and only if it's similar to some diagonal matrix, right? i.e., A is diagonalizable if and only if A is similar to some diagonal matrix. Okay. And these things are called similar matrices because somehow they behave similarly. The reason they behave similarly is because A and C, or C basically records what A does with respect to some different basis, just like in our diagonalizability example. If you pick a different basis, the basis whose vectors are B, then A acts like the matrix C. That's really what's happening here. Let me give you one example of a phenomenon where they're similar. Okay, so if A and C are similar, then A and C have the same eigenvalues. Right, they're similar, they behave similarly. One way is that they have the same eigenvalues. Okay, so let me give you a proof. And here, let me make a comment about the course. Okay, so this course does not require intro to proof. It doesn't require Math 300. It doesn't require CSE 311. So I'm not going to ask you on the homework assignments to write formal proofs necessarily. But even in Math 308, your professors ask you questions like, explain why this is true. Right? Justify your reason. Like, is this true or false? Justify your reasoning. Those are basically like what a little mini proofs really are, which is explaining why something is true. So on your problem sets, there will be lots of examples where you have to figure out whether something is true or not and then explain why. Also, you are all capable of understanding many proofs. They arose even in Math 308. So in lecture, I will definitely write proofs. It's not something to be scared of. A proof is just a logical explanation for why something is true. That said, it is kind of an advantage if you have seen the material in Math 300 and CSE 311. So for the last half of the lecture today, what I'm going to do is I'm going to go over a bunch of standard techniques for showing that something is true. And in fact, one of them is going to appear even in this proof. Okay, so the moral of the story is you don't need to be scared by the word proof. You do need to be able to understand things and explain to somebody else why those things are true by a convincing argument. That's all a proof is. Okay, so I'm going to prove that if A is similar to C, then they have the same eigenvalues. Okay, so suppose that A is similar to C. What does that mean? That means that there exists an invertible matrix B such that A equals B, C, B inverse. That's just what it means to say that A and C are similar. Okay, I want to show that A and C have the same eigenvalues. So suppose that lambda is an eigenvalue of C. What does that mean? Then there exists a non-zero vector x such that Cx equals lambda x for some, for that eigenvalue lambda. I want to show that actually lambda is an eigenvalue of A as well. Okay, but the point is that if A equals B, C, B inverse, then A times B equals B times C. Just multiply on the right by B on both sides. Right, so AB times X is the same thing as BC times X, because AB and BC are the same matrix. Okay, but now let's take a look at this a little bit more. BCX is the same thing as B times lambda x, which is the same thing as lambda times BX. Right, because C times X is lambda x. So if you consider what this equation is saying, it's saying that A times BX equals lambda times BX. Now, also, since B is invertible and X is non-zero, BX is also non-zero. Since X is non-zero and B is invertible, BX is also non-zero. That's one of the characterizations of an invertible matrix, is there's no non-zero vectors in the null space. So what do I have here? I have a non-zero vector BX that's, when you multiply by A, it's just scaled by the scalar lambda. In other words, lambda is an eigenvalue of A. Okay, so we just showed that if you have any eigenvalue of C, it's also an eigenvalue of A. Okay, and then what you can do is you can, instead of using B, everywhere where I used B, use B inverse. Everywhere where I used A, use C. Everywhere I used C, used A. Okay, so you can similarly, you can show, show that if mu is an eigenvalue of A, then it is also an eigenvalue of C. In other words, every eigenvalue of C is an eigenvalue of A, and every eigenvalue of A is an eigenvalue of C. In other words, A and C have exactly the same eigenvalues. Okay, and what we did at the end of the proof there is actually a really common technique in mathematical argument to show that two sets are equal, to show that the set of eigenvalues of A is equal to the set of eigenvalues of C. And so this takes me to the last part of the lecture today, which is I want to give you a brief overview of some common argument techniques that you might find useful as you're doing your homework and as you're following along with proofs in the class. Okay, so this is in section 1.5 of the Rovin-Thomas notes. It's called a quick primer on logic, or primer. Okay, and I'm actually going to start with the last one because it's the one that we just used. Here's the definition. We say that A is a subset of B. If A and B are two sets, we say that A is a subset of B if every element of A is an element of B. Okay? And one way to say that two sets are equal is to say that all of their elements are the same. Another way to say that two sets are equal is that they're subsets of one another. So to say that A equals B means that A is a subset of B and B is a subset of A. So if you want to show that two sets are equal, you can show that they are subsets of one another. So that every element of A is an element of B, and show that every element of B is an element of A. That means they're the exact same set. Okay, and of course, by the way, I should point out that you could also write this as A is a superset of B. You could also write it like that. Those are the same. Those mean the same thing. Okay, so how do you show this? Well, it's the technique that we just did in this proof. How did I show that? In the first half of the proof, what we showed was that the set of eigenvalues of C is a subset of the set of eigenvalues of A. We showed that every eigenvalue of C is an eigenvalue of A. How did we do it? We picked a fixed but arbitrary eigenvalue of C, and we showed that it was an eigenvalue of A. Okay, so to show that A is a subset of B, what you do is you pick an arbitrary element A in A and show that A is in B. Okay, by picking an arbitrary element, what I mean is the only thing you're allowed to use about little a is that it belongs to big A. So in this proof, I picked an eigenvalue of C, and the only thing I used about it was that it is an eigenvalue of C. So in other words, this argument would work for any of the eigenvalues of C, which shows that every eigenvalue of C is an eigenvalue of A. Okay, so the general technique, if you want to show that one set is a subset of the other, is you pick an element of A, an arbitrary element of A, and you show that it's also an element of B. Okay, so there's an even more concrete example in the notes, section 1.5. So if, for example, if A is a set of even numbers in some argument, and you want to show that this is a subset of some other set B, that A is a subset of B, what you do is you pick an arbitrary even number A. Okay, now you're not allowed to say pick 10, because 10 is not an arbitrary even number. 10 is 10. But in your argument, if A is an even number, then what that means is then there exists some other number, K. Oops. Sorry. A number K such that A is equal to 2 times K. And then you can use properties like this. So this is a property that's true for every single even number. So in your argument, you can only use the fact that A is an element of A. Okay, and then to show that A equals B, you just show that A is a subset of B and that B is a subset of A. Okay, so how do you show A equals B? You just do this argument twice. Show that A is a subset of B and B is a subset of A. This is a very standard common technique. If you're asked to show that two sets are equal, you show that they are subsets of one another. Okay, this is actually the last thing that's in section 1.5. The first bit of 1.5 is about proving or showing or explaining or justifying if-then statements. Okay, they're very, very, very common forms of statements in mathematics, and there's lots of examples all over the place, right? In the notes, for example, there's statements like if like x is, I mean, even something like if lambda is an eigenvalue of C, then of A or of C, then lambda is an eigenvalue of A. Right? This was just something that we just said in the last proof. And it's of the form if something, then something else. Right? Let me use different colors actually here. Let's call the statement P and call the statement Q. Okay, and you are often asked to show if P then Q. Show that if lambda is an eigenvalue of C, then lambda is an eigenvalue of A. Okay, so if P then Q is a very common structure for a statement. You can also say this means the same thing as P implies Q. If P is true, then Q is true is the same thing as P implies Q, or it's sometimes written like this. These all refer to the same structure of sentence. If P, then Q. Okay, P is called the hypothesis, and Q is called the conclusion. Okay, and very, very often in this class, we'll ask you to argue something like argue why, or show why, or justify why. If lambda is an eigenvalue of C, then lambda is an eigenvalue of A. And there are some very standard techniques. And here's the first technique. The first technique is called the direct method. So to show if P then Q, what you can do is you assume that P is true and show that Q must be true. Okay, again, this, like, when I'm writing it down like this in its chemical purity, it seems like it's kind of fancy, but that's exactly what we did in this proof here, and hopefully you followed this proof here. How did I show that every eigenvalue of C was an eigenvalue of A? I suppose that lambda was an eigenvalue of C, so I suppose that P was true, that lambda is an eigenvalue of C, and then I show that this forced lambda to be an eigenvalue of A. And that shows that if lambda is an eigenvalue of C, then lambda is an eigenvalue of A. This was just a proof using the direct method. I assumed P, and I showed Q. Okay, there is an example in the notes, which I think I have time for. Here's the example. Let me just start on a new page. So fix a matrix A, an m by n matrix A, and let S be the following set, the set of vectors x and Rn, such that a squared x equals ax. Right? Argue that if x and y are an S, then x plus y is an S. Something like this could easily appear on a problem set. Here's some setup. Argue that if x and y have this property, then x plus y has this property. How do you make this argument? First, you recognize that it's a if P then Q statement. How can you show this? You suppose that x and y are elements of S, and you show that x plus y must be an element of S. Okay, so in showing that this is true, what you do is you suppose that x and y are in S. Take two elements of of S. Now, what does that mean? That this means exactly that a squared x equals ax, and a squared y equals ay. That's what it means to say that x and y are both in S. And now what you can do is you can just add these two together. So adding these two equations yields a squared x plus a squared y equals ax plus ay. Right? Hence, if you take a squared times x plus y, by properties of matrix multiplication, this is the same thing as a squared x plus a squared y, because matrix multiplication distributes over addition of vectors, which is by the above ax plus ay, and again, now you can factor out the a. And what does this mean? This means that if you take this vector and multiply it by a squared, it's the same thing as this vector multiplied by a. In other words, this vector is an S. So this is a direct proof. I supposed the red bit, and I showed the blue bit. Okay, so that's sort of the most straightforward way, but there are other techniques that you have at your disposal, and one of these is called the contrapositive. Okay, so if you consider the statement, if P then Q, consider the statement, if P then Q, its contrapositive is the statement, if Q is false, then P is false. Okay, so in logic, you might say denote if P then Q like this. And to say that Q is false, you might denote it like this. This symbol, or sometimes a different symbol, means not. So this you could express as if not Q, then not P. Okay, and it turns out that the contrapositive says the same exact thing as the original statement. Let me just give you an example. Okay, so let's make the statement, if you get 100% of the points in the class, then you get an A. If you get 100 points, right? So let's let P be, you get 100% of the points. And Q be the statement, you get an A. Okay? Well, then if you do not get an A, it must mean that you did not get 100% of the points. So another way to express this is to say, if you don't, like anyone who didn't get an A, didn't get 100% of the points. That's exactly the same thing as saying, if you did get 100% of the points, then you did get an A. Notice that it's not the same thing as saying, if you get an A, then you got 100% of the points. Because maybe people who got 95% of the points also got an A. Okay, but it turns out that these two statements are actually saying the same thing. So if you're asked to show if P then Q, sometimes you can show the contrapositive instead. You can show if Q is false, then P is false, and that might be easier in some cases. Okay, so there is a nice example in the notes of the contrapositive. So here's the example. So consider the statement, if x squared minus 6x plus 5 is even, then x is odd. Okay, this statement looks kind of complicated because if you were trying to do this by direct proof, you would suppose that x squared minus 6x plus 5 is even. But then what do you do with that? That's like a complicated thing that's not so easy to work with. But if I ask you to show this statement, then you could instead show the contrapositive. So the contrapositive is, again, let me circle P and Q. The contrapositive is if Q is false, then P is false. So the contrapositive here is if x is even, then x squared minus 6x plus 5 is odd. And the contrapositive might be easier to show. In this case, it is easier to show because x is even is something very simple to work with. Okay, so if I wanted to prove this, what I'd say is suppose x is even. So I would say, actually, I will instead prove, or I will instead show the contrapositive. I will show the contrapositive. Okay, suppose x is even. What does that mean? That means there exists an integer k such that x is equal to 2 times k. Every even number is just 2 times some other number. Okay. Then x squared minus 6x plus 5 is the same thing as 2k squared minus 6 times 2k plus 5. That's just by a substitution. Which is the same thing as 4k squared minus 12k plus 5. Which is 2 times 2k squared minus 6k plus 5. And the point is that it's now clear that this is an even number because it's 2 times something. And this is an odd number, because 5 is odd, and the sum of an even plus an odd is odd. So x squared minus 6x plus 5 is odd, which shows that the original statement is true. Okay, so sometimes it will be very useful to be able to show the contrapositive instead of the original statement, and now I've told you that you're allowed to use the contrapositive. Okay, and then the last technique I want to talk about is called contradiction. Okay, so this is also a very effective technique. I'm giving you just 3 techniques, but you will find each of them to be very useful depending on the situation. Okay, so suppose that you want to show if P then Q. So we want to show if P then Q. If you want to show that this is true using contradiction, what you do is you assume that P is true and Q is false. So you want to show, what you want to show is if P is true, then Q is true. What this technique does is you assume that P is true and you assume that Q is false. In other words, you assume that you're in a situation that you never want to happen, right? Assume that P is true and Q is false. And then if you conclude a contradiction, in other words, a statement that's always false, then your assumption must have been false. So then you deduce a contradiction. In other words, a statement that is always false. And since you assume P was true and Q is false, and you deduced something that's always false, it must mean that what you assumed can never happen. In other words, it can never happen that P is true and Q is false, which is the same thing as saying if P is true, then Q has to be true. Okay, so let me give you the example from the notes. So consider the statement if x1 through xn is the basis of Rn. X1 through xm, potentially a different m, then m equals n. Okay, so again, here the statement P is this is a basis of Rn, and the statement Q is m equals n. Okay, so one way to show this is to suppose that P is true and Q is false, and come up with some contradiction, and that would show that the statement holds if P then Q. Okay, so suppose for contradiction that x1 through xm is a basis, and m is not equal to n. I want to show that something contradictory will happen. Okay, well, this means that either m is greater than n or m is less than n. That's what it means to be not equal. Okay, and there's 2 possibilities. So if m is greater than n, then we have more than n vectors in a basis of Rn. Right? Because the x's are supposed to form a basis, and I have more than n of them. But we have a theorem from 308 that any set of more than n vectors in Rn is automatically linearly dependent. But by math 308, any set of vectors more than n vectors in Rn is linearly dependent. But that means that our basis is linearly independent and linearly dependent, and that's a contradiction. So this basis x1 through xn, it's a basis, so it's linearly independent, and it's linearly dependent. Which is a contradiction. Okay, similarly, if m is less than n, then what we have is we have fewer than n vectors that span Rn. We have fewer than n vectors that span Rn. Or maybe I should say fewer than n vectors in a basis. Okay, but we have a theorem from Math 308 that says that fewer than n vectors never span Rn. But they're a basis, so they have to span Rn, which is a contradiction because they have to, but they don't. Right? Then x1 through xn, or xm, does not span Rn, but it does span Rn, since it's a basis. And that's a contradiction. So in either case, we derived a contradiction. So it must be that m can't be bigger than n, and that m can't be less than n. In other words, m equals n. Okay, so this was just a quick primer on logic because you will be asked to argue things, and it will be useful to have these tools in your toolkit as you argue them. Right? Of course, in general, the hard part will be the linear algebra, but we want to make sure that we're somewhat comfortable with these different forms of argumentation. Nothing here is super fancy, by the way. These things are covered in Math 300, but they're covered in the first day of Math 300, right? So that doesn't mean that I expect you to know them before this class, but you may need to use these kinds of arguments in your problem sets. Either the direct method, or proving the contrapositive, or perhaps using contradiction, and then of course showing that two sets are equal by showing that they're subsets of one another. Okay, so next time, what are we going to talk about? We're going to talk about permutations and the determinant, and your first problem set is due on Friday.